Okay, I'm going to talk about the intersection of a line and a plane. There are three different options, and I'm going to let the desk represent a plane and this meter stick represent a line. A line and a plane can be parallel and distinct, meaning that the line could hover over top or below the plane, but still be parallel, so it'll never pass through. The second option is the line is contained in the plane, meaning that the line could be one of the direction vectors of the plane. It lies parallel with the plane on the plane. In both of these cases, the dot product of the normal vector of the plane and the direction vector of the line will be 0. To test the difference, you just have to make sure that the point on the line and the plane lie within both the line and the plane. So if you know one point on a line, you test if it's in the plane, and you can do vice versa if you know a point in the plane. If they are in both, then the line is contained in the plane, and if they are distinct, then the point on the line will not be in the plane. Because if this point here is on this line, it isn't in the plane, this is parallel and distinct. The third option is when the line intersects the plane at a point. That would be something that maybe looks like this. That's when the dot product does not equal 0, and then you can determine that one point of intersection. If we look at our example, it says determine if the plane and line intersect. If they do, state the solution. So the first thing we need to do is identify which is the plane and which is the line. You should be getting a hang of this by doing a lot of practice problems. The equations do look similar, but this is the line because there is only one direction vector. And this is the plane because there is a z component to the scalar equation. The direction vector here is -2, 1, 3, and the normal vector here is 1, 2, -3. 1, 2, -3 being the coefficients in front of x, y, and z. So let's determine which of these three options we have by doing the dot product of n and v. It's going to be -2 times 1 plus 1 times 2 plus 3 times -3. This should get -2 plus 2 minus 9, which is -9. And now that we have that value, we know the line intersects the plane at one point. To determine that point, we change the line into its parametric equations and plug those parametric equations into the plane. X is going to be 3 minus 2t. Y is going to equal 2 plus t. And z is going to equal -1 plus 3t. Those are our parametric equations. Those x, y, and z values can be plugged into our plane equation so that t is our only variable. We can then solve for t and find our point. What I just did is plug the parametric equations in for x, y, and z in our scalar plane equation. I'm now going to expand across the brackets. Now I'll collect like terms, keeping t on this side and bringing all the constants over to the other. I have -2t plus 2t minus 9t will just leave me with minus 9t on this side. And I'll have 10 minus 3 will give 7, minus 4 will give, minus 4 will give 3, and then minus 3 will give 0, So negative 9t equals 0. So t equals 0. Meaning, if we substitute t into our line equation, we just find out that they intersect at the point 3, 2, negative 1.